All right, let's do a mechanics 3 example. So this is an AP question. Now, interesting enough on this one, there's 2 ways to solve it. So let's go ahead and read the problem, and then I'll show you both ways we can solve part A and B. So it says a thin hoop of mass m and radius r and rotational inertia mr squared, so we know the moment of inertia for this, is released from rest at the top of a ramp of length L. Okay, the ramp makes an angle theta with respect to the horizontal tabletop to which the ramp is fixed. This table is at a height h above the floor. Assume that the hoop rolls without slipping. Rolls without slipping, that tells me that the linear speed that the hoop is moving at is equal to the angular speed times the radius it's rolling on, which in this case is its radius. Express all algebraic answers in terms of the given quantities and fundamental constants like g for acceleration. So part A says derive an expression for the acceleration of the center of mass of the hoop as it rolls down the ramp. Part B says derive an expression for the speed of the center of mass of the hoop when it reaches the bottom of the ramp. So the idea here is that speed and acceleration and L are kind of all related through 1D motion. And so you can choose to do this one of 2 ways. You can find the speed at the bottom and then do a 1D motion problem to find the acceleration. That would be the way where we do B first, then A. Or we can do A first, where we find the acceleration, and then do B second, where we find the velocity at the bottom using 1D motion. So I'm going to show you both methods. The second method that I'm going to show you with work energy theorem is probably the more common and easier to do method, but I still want to show you this first method with forces and torque, so you know how to do this if you need to in that case. All right, so our first method, we're going to use forces and torques to go ahead and find the acceleration. Now get this, there's 2 ways to do this one too, so I'm going to show you both of those as well. So the first scenario, we are going to go ahead and use the center of mass as our axis of rotation. We won't have to use the parallel axis theorem. We already know the moment of inertia if we choose that as our axis rotation. The second method I'm going to show you here, we're going to go ahead and choose our axis at a different location. So to do the forces and torques method, the first thing I need to do is draw my free body diagram. So I have mg, and so you'll see that mg is not producing any torque because it's located at the axis of rotation. I have a normal force pointing perpendicular to the surface, and so I see that the normal force is along the radial line, so also not producing any torque. So the only thing actually producing the torque is that force of friction, which we don't know any information about that force of friction, so we are going to have to solve for that elsewhere. All right, so let's go ahead. We're going to generate a torque equation. So the sum of the torques is going to cause this to angularly accelerate. And I'm going to go ahead and rotate my coordinate system here. And so this is my x, this is my y. So it is going to linearly accelerate in my x direction. So the sum of the forces in the x is going to be ma. And because it is rolling without slipping, I'm able to link the angular acceleration and the linear acceleration. So because we're rolling without slipping, I can link these 2 together. I can say that A, the linear acceleration, so like ACM I guess you would say, is equal to alpha times the radius it's rolling on. So you can imagine that other equation where we say the linear speed is equal to the angular speed times r. So if I just take the derivative of that equation, I have this one. So that's going to allow us to link these 2 equations together. And so let's go ahead and set this up. So my torque equation only has the force of friction times the radius. And you might ask, well, what about the direction of that torque? So it's causing a negative torque. But in order to have this equation work here, this is the direction of my acceleration. That is my positive direction. I also need this then to be my positive angular direction so that this equation works out. So just the same as when we do multiple masses, we need to identify the acceleration of both and make those both positive so our equations work. So this will be a positive torque because it's in the direction of my positive direction. I can make my substitution, mr squared. Alpha, I can make my substitution that it's A divided by R. The big benefit here is what happens to all those R's is they all cancel. That's a big benefit. All right, now I need to create my X equation. So I need to go ahead and resolve mg into components. And so I have mg sine of theta here, pointing down the incline, force of friction up. So I'm left with mg sine of theta minus the force of friction equals ma. I know what the force of friction is. It's also equal to ma. So now I have mg sine theta minus ma equals ma. Fantastic. All of the all of the masses cancel. Move that a over to the other side, so now I have g sine theta equals 2a. So now I know my acceleration is going to be g sine theta divided by 2. I should double check to make sure these are the given quantities that it told me about. So it told me about the angle and other fundamental constants, so that's g. Now I can set up my 1D motion problem. So for my 1D motion problem, I know the initial velocity is 0. X naught x, v naught v, a, and t. So I'm trying to find that final velocity. I know this is going to be my g sine theta over 2. And I know that it's going to travel a distance L in my positive x direction. So I'm just trying to find the final velocity, equation without t. So I have v squared equals v naught squared plus 2a x minus x naught. Cross out anything that is 0, and so I'm left with v is equal to the square root, plus or minus, but it is plus because it is moving in my positive x direction, 2 times the acceleration, which is g sine theta divided by 2, times my distance, L. I see my 2's cancel, and so I'm just going to write my speed as being gl sine theta, all within the square root. So I've found my acceleration for part A, and I found my speed for part B. All right, so let's go ahead and reset this and solve it using a different axis of rotation to see how that torque and force equation looks. Okay, so now we got it reset. So now we're going to choose our axis of rotation at a different location. We're going to choose it down here. And you might say, well, why are you going to do that, Mr. Foster? Well, let's draw our free body diagram and find out why. So my normal force acts from that point, so it is not producing any torque. My force of friction also acts from that point, so it is not producing any torque. So the only force actually producing any torque is mg. So mg is going to produce some torque. We're going to have a component that points radially. That one isn't producing any torque. But the component that points perpendicular, this one, mg sine theta, is going to be producing torque at that point. And so it makes my torque equation, the sum of the torques equals I alpha. And you'll remember, because it says derive at the start of this, that I do need to start with Newton's second law. I do need to show this. I can't just jump to the next equation I'm about to write. So I have mg sine alpha, sine theta, times its distance away, r, equals I alpha. Now the thing that's going to be different here, it's still rolling without slipping, so I can make this connection that alpha is equal to a divided by r. But my moment of inertia that I had here was about the center. So I'm going to need to find the moment of inertia about the edge. And so I'm going to use the parallel axis theorem for that. So the moment of inertia about some point D is ICM plus md squared. And so in our case here, it's going to be mr squared plus m times the distance between the two, r squared. So my moment of inertia is just going to be 2mr squared. Now I can make some substitutions. So I have mg sine theta times r equals I, which is 2mr squared, times alpha, which is a divided by r. And at this point, we should see a whole bunch of stuff start to cancel out. So my m's cancel, my r's all cancel, and so then I just need to divide the 2 over to get a by itself. So I'm left with g sine theta divided by 2 equals a, and I'm there. Same setup as I did in the last example for finding 1D motion and finding the final velocities. Okay, so let's set this up yet again, and I'm going to show you the work energy method to find the speed at the bottom and then work backwards through 1D motion to find the acceleration. So let's go ahead and set that up. All right, so now we're set up for the work kinetic energy. So we're going to do part B, then part A. Again, I'm showing you 3 methods here to do the first 2 parts. You can choose whichever one you want, whatever one makes sense to you. So for the work kinetic energy, I see that my ball is starting at one point, or my hoop, I'm sorry, and it's ending at another point. That means I can use the work kinetic energy theorem. Now, with the derive aspect of this, I should write out my whole work kinetic energy theorem. I have seen when I do the grading that they'll show in their answer keys that they just kind of skip that first step where we cross everything out. I'm going to write it just to be extra careful. So I have work in plus work done by friction equals K2 minus K1 plus UG2 minus UG1 plus there's no springs. All right, let's cross out some more stuff, shall we? No one is pushing on it. It's moving at the bottom, not at the start. The height at the bottom is going to be 0. The height at the top is not 0. Now I do have one more up here, work done by friction. And there is friction because it's rolling without slipping. Now we do have to be careful here because work done by friction, work is force times displacement. And the only way that friction can do work is if there is displacement, if there is sliding. And so there is no sliding, no displacement, so that is going to be 0. All the friction is really doing is helping take this potential energy and convert it into both rotational and translational kinetic energy, kind of split that energy up. All right, so writing this out, I got 0 is equal to, now kinetic energy is both 1/2 mv squared plus 1/2 I omega squared. We have both rotational and translational kinetic energy minus mgh. Okay, because it's rolling without slipping, that means this omega and this v are related. So V is equal to omega times R. All right, so let's make some substitutions here. So I have 0 is equal to 1/2 mv squared plus 1/2 I, which was mr squared, times omega, which is going to be v over r, but it's omega squared, so it's v squared over r squared minus mgh. These r squareds cancel. I also see that the m's all cancel. Fantastic. And so I can move this GH over to the other side, is equal to 1/2 v squared plus 1/2 v squared just gets v squared. And so I end up with v is equal to the square root of g times h, but my h was L sine theta. And so I'm going to get that same velocity I got the other methods. Now I just need to work backwards through 1D motion to go ahead and find that acceleration. So x naught x, v naught v, a, and t. So we start at 0, we go to L. It starts at rest. It ends at the square root of goal sine theta. And I'm trying to find the acceleration. I don't care about time. So we're going to go ahead and use the third equation here. So I have v squared equals v naught squared plus 2a times x minus x naught. Cross anything out that's 0. Solve for a, so it's going to be v squared divided by 2x will give me my a. Plug in my values, so now I have gl sine theta divided by 2 times x, which is L. The L's cancel, and so my acceleration comes out to be g sine theta divided by L. One thing to note here, both of these, L theta, oops, that's a 2 on the bottom, not an L. These are all the terms that they want me to use. All right, let's set this up and we'll do section C and D. Okay, so we're set up for part C. So derive an expression for the horizontal distance from the edge of the table to where the hoop lands on the floor. So this looks like it's going to be 2D projectile motion. We know this speed from part B. Now let's say I bombed part A and part B. I didn't get the answer. What I can do is I can just say this V. Just give it some quotes. It's not one of the terms they used, but I'm going to say V found in part B. They're still going to give me partial credit for solving this part of the problem, even if I didn't solve part A and B. All right, so let's set up our 2D motion here. So I'm going to have x naught x. All right, so I have that set up. So I'm going to go ahead and start plugging some information in. So because it's projectile motion, the acceleration in the x direction is 0. These are all x's. Meters per second squared. And in the y direction, it's negative g. Because this is 0, these two values will be the same. And it is this number that I just solved for, the square root of GL sine theta. Now I'm trying to find this x value here. This starts at 0. It starts at a height h. This was given to me in the problem. Ends at a height of 0. Initial vertical velocity was 0 because it was horizontally launched. So what I want to do is I want to pick an equation that doesn't have the final vertical velocity in it to solve for time. Once I get time, I'm going to plug time in over here and solve for x. So let's go ahead and do that. So I'm going to pick an equation without v final. That would be equation number 2. So I have y equals y naught plus v naught yt plus 1/2 ay t squared, crossing off things that are 0. And so I'm left with 0 equals h plus 1/2 times negative g t squared. Move the h over, cross out the negatives, multiply by 2, divide by g, and take the square root. So my time will equal the square root of 2h over g. Now I have my time in terms of variables that they gave me. Now I'm going to plug that in over here. Whenever you have an acceleration of 0, you're always stuck with equation number 2. So x equals x naught plus v naught xt plus 1/2 at squared, which is 0. It starts at 0. I am solving for x, so I just need to plug in my information. So I have the square root of GL sine theta times my time, which is the square root of 2h over g. I can combine these together, and when I do so, you'll notice that the g's are going to cancel. And so I have the square root of 2hl sine theta will be my distance it lands away. So let's hit the last one. So suppose that the hoop is now replaced with a disc with the same mass and radius r. How will the distance from the edge of the table to where the disc lands on the floor compare with the distance in part C? So now that I have a disc, okay, so what did we do? We made the moment of inertia smaller by making it a disc. So we made that less energy needs to go into rotation, so more energy can go into translation. So this number will be larger, it'll be moving faster, and therefore it will land further from the edge of the table. Now, you have two options here. I'm not going to show the second option, but what you could do is you could go back through, plug in your 1/2 mr squared for your I, calculate your final speed, and then recalculate this distance down here, and you'll get a value that is 8/3 here instead of 2. And so then you can say, okay, it's going to come out to 8/3 hl sine theta if we do that with a disk. And I can say that 8/3 hl sine theta is greater than 2 hl sine theta, and therefore proving it. So you can either write it out in words, so talking about how a larger moment of inertia, less energy needs to go into rotation, more energy for translation, therefore it'll be moving faster. If it's moving faster, it'll land further. You can write it in words, or you could just calculate it and say, hey, it's more than that. We're good. All right, there you go. Holy cow, that was a long one.